Hi, good morning. I'm Xiaoxiao Li from Yale University. So today, I would like to share my work about ASD biomarker detection by analyzing deep neural network. Firstly, I want to introduce the background of my project. Autism spectral disorder is a range of complex neurodevelopmental disorders. It emerges in early life and generally associated with lifelong disability. And fMRI, I don't think I need to introduce too much about it. And it's an important tool to investigate ASD. And recently, deep neural network has already been applied on fMRI data to identify ASD and achieved relatively good results. However, the clinicians typically want to know if the DNA model is trustable and how to interpret the result. So motivated by this, we proposed a two-stage pipeline. So at the first stage, we train a deep neural network classifier to identify ASD versus control. And in the second stage, we want to find the biomarkers which was activated by the deep neural network classifier that used to the classification task. Before I go into the methodology, I want to introduce the data we used. For the both ASD and the control group, we asked these two groups watch these two videos under the fMRI scan. So in the video on the left, you can see the dots move like human beings. And for the video on the right, the dots just follow some random movement. So we suppose that for the ASD and the control subs, they may have different brain activity when they watch these two videos. And we collected 82 ASD subjects and 48 healthy controls. And they are IQ and age matched. And for the raw fMRI, we did this kind of pre-processing: motion correction, timing correction, brain extraction, spatial smoothing, and temporal filtering. And also, we examined the motion effect and found that there is no significant difference between the group. And firstly, once we collect data, how can we train a classifier using the fMRI data? So we propose, so firstly, you can see this is the original 4D fMRI here. Firstly, we apply a sliding window along the time axis. And in each sliding window, we calculate the mean and the standard deviation. We calculate the mean and standard deviation of each voxel in the 3D volume. And in this way, in each sliding window, we generated a mean 3D volume and standard deviation 3D volume, which has the same size as the fMRI input 3D volume. And since the sliding window moving along the time axis, actually we generate a sequence of mean channel image and the standard deviation channel image. And these two combined channel image will be used as an input for our deep neural network. And in these slides, I would like to introduce the architecture we used for classifying ASD and control subjects. We call it two-channel convolutional 3D deep neural network, in short, 2CC3D. 2CC3D has 6 3D convolutional layers and 4 max plane layers, followed by 2 fully connected layers. As I mentioned before, the mean channel and the deviation channel will be used as the input of the classifier. And for the output, we set a threshold here and generated the binary output. Since for each subject, it has a sequence of mean and the standard deviation pairs, so actually the output is a list of zeros and ones. And for the final decision for a single subject, we did majority voting. And here are the more details of the parameter settings for the network. And at the end of the day, since we have the unbalanced data set, we use F-score to measure the performance of our classifier. And as you can see here, we compiled our deep learning method with traditional machine learning methods, such as logistic regression, support vector machine, and the random forest. And you can see here our 2CC3D model outperformed the traditional machine learning method. After we trained a highly accurate classifier, actually we want to know what regions or what biomarkers this deep neural network were used as indicator to make the final decision. So we propose a second stage. Firstly, how we generate a cropped image as the input for the neural network. We populate the brain into 150 regions. And then for robustness, we aggregate, blacking out with zeros and adding Gaussian noise to crop a region of interest, which you want to verify whether this is an important brain region for identifying ASD. And we will do this kind of corruption, ROI by ROI, examine the whole brain ROIs. Oh, sorry. And for the first stage, you have seen the output of our deep neural network, like this kind of distribution. Then we also generated a cropped image. How can we make the comparison between the original distribution and the cropped distribution? First step, we want to test whether the cropped image follows the classifier. What does that mean? So here, to make it simpler, I draw a simple graph here. From the classifier, we basically generate this kind of two distributions from our input from two groups. We define the distance between these two distributions using the Jason-Shannon divergence. And here KL is defined by this equation. We calculate the original distance of the two distributions, and then we also calculate the distance after cropping. And then we will claim that if the distance of the cropped distribution is smaller than the original distance, that means these two distributions get closer. We will say our corruption strategy for the classifier. And then we want to test whether the shift is significant. So we use wheel constant test method to test the shift significance. And also, since we have two corruption methods, if both corruption methods make the shift to the same direction, we will say the cropped region is a saliency ROI. And further, when we say these two distributions, they get closer, actually there are three scenarios. As is shown in figure B, the first scenario is that these two distributions get closer to the middle. And for figure C, the green one kind of fixed and the pink one shift to left. And for figure D, you can see the pink one is kind of fixed and the green one shift to right. And based on these three scenarios, let's say the green one is control and the pink one is ASD. We will say that in case B, the ROI contain important features for identifying both ASD and control. And for scenario C, we can say that this ROI has patterns associated with identifying ASD. And for scenario D, we can say this ROI contains features with identifying control subjects. And here's the result we found. So for the blue regions, which means it's important for both regions, we found that these regions are significant related to executive and attention. And for the red regions, which are associated with identifying ASDs, we found these regions as associated with emotion. And for the green regions, which are associated with identifying control, we found most of the regions are visual-related regions. And in summary, we designed a two-stage pipeline to detect brain biomarkers for identifying ASD and the control subjects. The aggregating method robustly detected the brain regions activated by the classifier and grouped the biomarkers based on the shift of the outcome distribution. And our method was designed for interpreting important ROIs for the register images. So that means you can apply this method to any other kind of neural disorder disease and learn the features that the deep neural network used. And finally, our proposed method can directly used to interpret any machine learning classifiers So no matter what deep neural network you use or machine learning classifier you use, you can apply this approach to analysis the biomarkers. And I would like to thank my lab mates at Yale, and for these pictures, they are the co-authors, and they cannot come here. And also, this project is funded by NIH grant. Thank you for your attention, and my email and the WeChat QR code are listed here, and I'm more than happy for further discussion. And recently, we have implemented more accurate deep learning architecture and interpretation pipeline. So I'm happy to share my recent work with you, and feel free to stop to my poster, 2512. Thanks.